The inspiration for works of art comes from all sources, including the mystical. But there is nothing mystical about the fact that many classic forms of art can be modeled using mathematical equations. Hi, my name is Tom Atwater, and today we will be looking at formulas for volumes of solids in 3 dimensions. Now, earlier in the book, we estimated the volume of a sphere by partitioning it into thin slices that were nearly cylindrical, and then summing those cylinders' volumes using MRAM, that is, Riemann sums, which we now have learned can be expressed as a definite integral. We will apply this concept to finding the volume of solids by integration. So let's take a look. Let's say we have this particular solid. What we're going to do is take a cross-section of it, and in my next screen, we're going to blow up that cross-section and take a look at the fact that it's a cylinder and that we can approximate that area using the base of the cylinder, which, of course, is going to be a circle. And we can then integrate with respect to x as delta x goes to 0. For the sum of the Riemann sums, it turns into the integral and gives us the following fact, that the definition for the volume of a solid of known integrable cross-section, area A of x, from x equals a to x equals b, is the integral of a from a to b. And there we have the volume is the integral of a to the x dx evaluated from a to b. So what we're saying is that the volume is simply the integral of that area with respect to x. So let's take a look at the method of doing this. First thing, sketch the solid and a typical cross-section. And a sketch is plenty good enough. It doesn't have to be an exact diagram. Then find a formula for the area of that cross-section. Find the limits of integration, and then, of course, integrate that cross-sectional area to find the volume. Let's look at an example with a square cross-section area. So here we have the solid lies between the planes perpendicular to the x-axis at x equals 0 and x equals 4. The cross-sections perpendicular to the axis on the interval from 0 to 4 are squares whose diagonals run from y equals negative square root of x to y equals the square root of x. So what we want to do is figure out what the area of this square is. Well, if the diagonals run from y equals the negative square root of x to the square root of x, then a diagonal would be equal to the square root of x minus negative the square root of x, which of course is 2 square roots of x. So that's the diagonal. And from the diagonal of the square, we can say that the area of the square will turn out to be 2 times x. So let's go and set up that integral for the volume. The volume is going to be equal to the integral of the area of the square, which we said was 2x and dx, and we know that the limits of integration are from 0 to 4. And so we integrate this. We get x squared evaluated from 0 to 4, which will give us 16 cubic units. So there's an example of finding the volume by integrating the area, and the area was a square. Now let's look at a circular cross-section area. So we have the example. Find the volume of the solid generated by revolving the shaded region about the x-axis. And here's our diagram. What we have is the line right here of x plus 2y equals 2. And so what we want to do is solve that for y. So y would equal 2 minus x over 2, which is 1 minus x over 2. We can see that our limits of integration are going to go from 0 up to 2. And that when we take this line and revolve it around the x-axis like this, we're going to make a cone. And I don't have enough room, but I could show at least part of the other side of the cone, so that, of course, we will have this as a circle. That would be our cross-sectional area. So what we're interested in is, of course, r, the radius. Well, that is y minus x over 2. So the cross-sectional area is a circle. Pi r squared is the area of a circle. R, in this particular case, is 1 minus x over 2. So let's set this integral up. We would have that the volume is equal to the integral from 0 to 2, those are our limits of integration, of that area, pi r squared. So it's pi, and remember, r was just the function, 1 minus x over 2, so pi r squared dx. And now we need to integrate that, and I used the calculator and init, and my function, of course, was pi 1 minus x over 2 squared, comma, x is the variable, and my limits are 0 and 2. And when we work all of that out, we will get an answer of 2 pi over 3, and again, it's cubic units. We are going to explore a cross-section that is a circular region with a circular region cut from its center, or in other words, a washer. It looks like this. And what we have then, of course, is an inner radius of r, and the radius of the larger one I'll use as big R, or capital R. And so if we want to find that cross-sectional area, we would take the area of the outer circle, pi r squared with capital R, and we would subtract the area of the inner circle, which is pi little r squared. And I can simplify that a little bit into r squared minus r squared in parentheses, quantity times pi. So that would be how we would find the area of a figure in which part of the center is cut out, and we're using cross-sectional areas. So what we're going to do now is apply this concept to an example. So let's take this example. Find the volume of the solid generated by revolving about the x-axis the region bounded by y equals x squared plus 1 and y equals x plus 3. Let me draw a diagram with these graphs on it. We have y equals x squared plus 1, which is a parabola opening up, passing through a y-intercept of 1. Then we have y equals x plus 3, which would be the line with a slope of 1 and a y-intercept of 3. This point over here, that point of intersection, would be the point -1, 2, which means that our limit of integration starting with x equaling -1. Over here, this point of intersection is 2, 5. So that limit of integration for x would be 2. The area that we're going to revolve around the x-axis is this area right here. So you can see that as we revolve it around this axis, we will be missing the center portion, right, as it revolves around. So that's where the idea of this washer comes into play. The upper curve, y equals x plus 3, would be our capital R. The lower curve, x squared plus 1, which is right here, would be the little r when we plug this into the formula pi times capital R squared, which would be this, minus little r squared, which will be that. So now, let's set up that integral. So we have the integral from -1 to 2 pi times capital R squared, so x plus 3 squared, minus little r, x squared plus 1 squared, and that's all with respect to x. When we work this out in terms of expanding the binomials, we will still have the integral from -1 to 2 pi times negative x to the 4th minus x squared plus 6x plus 8. And of course, let's put that into the calculator, n int, which remember on the TI-84 is fn int, but we put in our negative x to the 4th minus x squared plus 6x plus 8. It's the variable x, our limits of integration -1, 2, and when I get this answer, it's 23.4. But then I have to multiply that by the pi, which I have not included in my n int, and we'll get an answer that's equal to 73.51. And that would be then the cubic units for that volume, which had a cross-sectional area of a washer, using the formula of pi times capital R squared minus little r squared. Well, there is a method for finding volumes that is useful when the axis of revolution is perpendicular to the axis containing the natural interval of integration. Instead of summing volumes of thin slices, we sum volumes of thin cylindrical shells that grow outward from the axis of revolution, similar to tree rings. Let's look at an example where we can use this method. The region bounded by the curve, the x-axis, and the line, bounded by the y equals the square root of x, the x-axis, and the line x equals 4, is revolved about the x-axis to generate a solid. Find the volume of the solid. Let's look at a diagram to begin to understand this. We have the graph for y equals the square root of x, and it's written here as x equals y squared. And so that's the blue graph. And what we're going to do is we're going to revolve this around the x-axis, as you can see the arrow here. And we're going to create a cylindrical shell. The thickness is dy. The shell height is given by the formula 4 minus y squared, which comes from our original function. So now what we're going to do is look at the actual cylindrical shell in three-dimensional form. Okay, so here we have it. You can see that here's that thin shell that I'm talking about, and it's created by revolving it around the x-axis. We have our limits of integration, as you can see with respect to y, are from 0 up to 2. And again, the shell height was created because we started here at 4, and we subtracted, well, now it's written as y equals the square root of x, but remember that's x equals y squared, so it's 4 minus y squared to give us the height of this cylindrical shell. The radius, of course, is just our y value. So we have the radius, we have the height. Now we can set up our integral in the following manner. We would have the integral for the volume evaluated 0 to 2, and now 2 pi times the shell radius times the shell height. And this will all be, of course, with respect to y. So what we now have is, plugging those formulas in, 2 pi times the radius, which we said was y, times the height, which we said was 4 minus y squared. And again, that's all with respect to y. So when we integrate this, we'll have 2 pi on the outside. We would have 2y squared minus y to the 4th over 4. And that's evaluated from 0 to 2. And when we evaluate that and work it all out, we would get that it's equal to 8 pi. So that's an example of where we can use what are called cylindrical shells to find the volume. Well, we're going to take a look at another example where we have a different type of cross-section. A mathematician has a paperweight made so that its base is the shape of the region between the x-axis and the one arch of the curve y equals 2 sine x. And that's measured in linear units, in inches. Each cross-section cut perpendicular to the x-axis, and hence to the xy plane, is a semicircle whose diameter runs from the x-axis to the curve. So you can think of the cross-section as a semicircular fin sticking up and out of the plane, and here's the picture of what we're looking at. We want to find the volume of this particular shape. And what we see is we have the curve right here, which is y equals 2 sine x. Then these fins that are created, that are in red, are semicircles, each one of them, where the radius is equal to that function y equals 2 sine x. So since it's a semicircle, then the radius would be half of the function. In other words, it's going to work out to be that the radius is sine of x. So when we go to set up this integral, which because the cross-section is half of a circle, we would have 1/2 of pi r squared, and this would be our r. So let's set up that integral and using that information. So it's going to be the integral from 0 to pi of 1/2 pi r squared, and r is the sine of x. And that's being integrated with respect to x. So what we have is, of course, throw this into the n int, and remembering that we still have the 1/2 pi outside of this, and our function is sine of x, which we should put in parentheses, squared. X is our variable, 0 to pi is our limit of integration. And when we plug that into the calculator, multiply by the 1/2 pi, we'll get an answer of 2 47/100ths. So there's an example of, again, using the cross-section of a semicircle, which just means we had to add in the 1/2 with the pi r squared. Well, you should clearly see that finding volume of solids can be artistic as well as fun and mathematically challenging. Well, now it's time for you to try a problem. So let's take a look at finding the volume of the solid analytically. The base of the solid is the region between the curve y equals 2 times the square root of sine x and the interval 0 to pi on the x-axis. The cross-sections perpendicular to the x-axis are equilateral triangles with bases running from the x-axis to the curve as shown in this figure right here. So what you know is that the base of this triangle is given by 2 times the square root of sine x. These are equilateral triangles. And so when you want to find the height, based on the full base being 2 times the square root of sine x, I will leave that up to you to figure out what the height is and then set up the integral. So pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, let's find out how you did on this particular problem. I'm on this screen because you had to calculate the height, and I hope that you found that the height, I'll put it over here, that the height was equal to the square root of 3 times the square root of sine x. And so now we have the base and we have our height, so we can set up our integral to find the volume. So let's do that. It would be the integral from 0 to pi of 1/2 the base times the height. And we said that the base was 2 times the square root of sine x. The height was the square root of 3 times the square root of sine x. And that's all with respect to x. And actually, this simplifies because we can cancel those to 1, and we have the integral from 0 to pi. Well, we still have the square root of 3, but now these simplify to sine x dx, which of course means that we have the integral is negative the square root of 3 cosine x. And we're evaluating that from 0 to pi. And in that case, we'll get an answer of 2 times the square root of 3. So that's the answer that I hope you got when you worked on this problem. Great section today. So what we talked about today is volumes as integrals, using cross-sectional areas that ranged from triangles to squares to washers, as well as using cylindrical shells. Be sure to work the exercises that your teacher assigns, and we'll see you next time.